Good morning, everyone. This video is intended to facilitate the learning process for week 3, all about the normal distribution and standard normal curves and z-scores. Uh, if I had my way, we would probably spend 3 or 4 weeks, maybe half of the term, just on this set of concepts. They are very powerful, and it's at this point that I mean, in earlier weeks from our online discussions, I can tell that you are connecting the dots between sort of what we cover in this class and how it could be useful for you in your place of business or in your organization. I've received many email messages and verbal comments by phone about how helpful some of the stuff has seemed to you, even when I show you how to use different parts of Excel, step by step, as one student said, Barney style. Um, but I hope and expect that that light's going to go on even brighter as we work through the assigned problems and a few others for week number 3. Um, the central limit theorem to be discussed in week 4, combined with these two concepts, or the concepts that we cover in week 3, are just really, really potent. And so I'd like to do this step by step. I'm going to give you this template just the way I have in prior weeks, and this will probably be one of 2, maybe 3 videos that I'll publish for the week. My assumption is that you've already spent some time with the material in the textbook, um, but that I don't want you to read that material more than once or twice. I just want it to be sort of background information for you. You won't probably really understand this material until you use it, tackling the problems that I've assigned. I guess I could say that about all of the material that we cover in this class, but it's especially true of this material. So, in this spreadsheet, the way I've organized it is the first tab is an overview. The second is the work that we'll do for question 1 on receipts. That it should look familiar to you. We already did some of this in a prior week. The next tab is about IQs and question 2, and then serial boxes, question 3, then paternity, and then work arrivals. Now, work arrivals, we're not going to use the standard normal distribution. We'll use something called the uniform distribution. So as you open this up, it's blank, but I'll explain that later. And then the last tab that I need you to complete is question 6 about your paper topic. Just give me a paragraph or so on your initial ideas of what you might research. In this video, I think we're just going to cover probably the overview and the first 2 tabs, and then in future videos we'll try to cover the other ground. This tab here that says additional practice, I want to get at that in the last video. You can review this, but it's in a way it's kind of like a quiz or a way for you to know whether you really understand the material or not. You won't have to submit this for grading or anything. It's just some extra practice. That's why I call it additional practice. There's several questions here having to do with the material. This last tab I don't want to talk about now, and I don't want you to look at it yet. It's something I just pulled off of Wikipedia. It's what I thought is a stats tattoo. If you were going to get a stats tattoo, that might be one. But let's save that for the end. Don't look at it now. It'll be maybe more confusing than it needs to be right now. So let's go to the overview. In this week, we're going to be looking at these bell-shaped curves and trying to focus on specific examples of where we have data that's normally distributed. In our discussion for the week, you have already identified many data sets that are likely to be normally distributed. Pretty much anything in nature, body weights, heights of adults or infants, um, the size of leaves on a tree, or the speed of different animals. I mean, imagine that we had 50 different jaguars, and we wanted to look at what their average speed was. If we started tracking this, we would end up seeing these bell-shaped curves. They're very useful because um, it tells us that most of the people or most of the units in the data set have a certain average, but then some are a little bit lower, some are a little bit higher, and then as we get on the tails of the curves, we get what we call outliers. IQs, for example, are normally distributed. The average happens to be 100. In an overall population of people in a given country or around the world, mu, the average for the population, would be 100. But we would have some who are much, much smarter. Their IQs would be over here. And we would have some who had much, much lower IQs. Not many, though. What's powerful about the material we're going to cover here is that we don't have to guess at exactly how many that is. In a given population, I could tell you precisely how many people would have IQs that would be above 145, for example, or below 55. We'll talk more about that later. So this thing here is called a standard normal curve. Standard because right now we don't know what the mean is. We just have the Greek letter mu, and you'll notice that it's segmented. One standard deviation below the mean, one standard deviation above the mean. Sigma is used to denote standard deviation. Again, this goes back to what you may have heard before the class, 6 sigma quality. Well, this graph shows 3 sigma limits. 3 standard deviations above the mean, 3 standard deviations below the mean. See the graph above, where the center of the curve is 0 z's. When we talk about z-scores, we're talking about how many standard deviations away from the mean it is. So this center line would be what we call 0 z's. This line here would be 1 z, or 1 standard deviation. This would be 2 z's and 3 z's. This graph here we're going to use to compute the exact percentages and the specific answers to questions that were assigned in conjunction with this other file that I gave you. This is a sample of a standard normal curve. I'll explain this as we go. Our textbook doesn't have it, so I stole this from another textbook. Our textbook wants you to use the handheld calculators. I'm going to show you a different way using these tables for now, and then when we're all done, I'll show you a way to get these answers without a table and without a handheld device and without even Excel. I'll show you how you can do that in the future if you need to. The empirical rule is really important to your understanding of what we're going to do this week. It says that approximately, that's this, it says, first of all, if we have a data set that's normally distributed, and we might have to check for that, grab some data and then we plot it out, see if we have a bell-shaped curve or not. If it is normally distributed, as so many data sets are, I spoke with a student a couple days ago, I suggested even if she pulled data from her place of business, the number of people who were paying their bills on time or a little bit late or a little bit early, that too would be normally distributed. Data sets like that tend to end up being bell-shaped when we have when the data set's large enough, over 100 or 1,000 units, we end up seeing a lot of bell-shaped curves. When we do, 68%, approximately 68.3% will fall between those 1 sigma limits. If you look on this first graph here, 68.3% of the data will be in this center of the curve. Approximately 95.4% will fall between plus or minus 2 standard deviations, plus or minus 2 sigma limits. And almost all of the data, 99.7%, will always fall within plus or minus 3 standard deviations. This is why we call it the empirical rule, because it actually works in practice, outside the classroom. It's empirically true that data ends up falling this way. So if you tell me that your IQ or your exam score is, let's say, more than 3 standard deviations above the mean, that's pretty exceptional. That happens less than 1% of the time. In fact, it happens less than 0.5%. Look at this last idea here. It says 99.7% of the data fall within 3 standard deviations of the mean. That means that only 0.3% would be in either of these tails. 0.3%. So 0.15% would be in this tail, and 0.15% would be in this tail. We notice that these curves are symmetrical. So if 99.7% fall between 3 standard deviations, plus or minus 3, it means that the remaining 0.3%, that means less than 1%, the remaining 0.3% would be in one of these tails outside of 3 sigma limits. 0.3% divided by 2, because there's 2 tails, is 0.15%. So 0.15% would be in this tail, and 0.15% would be in this tail. It's a very, very small chance that that we would see any data points there. So how might we apply this kind of? Well, one student said, should I be worried about my score on an assignment or in the class? My answer, if your score is less than 2 standard deviations below the mean, then that's a red flag. That should happen only, less than, well, look at the empirical rule again. 95% of the data is between plus or minus 2. So if you're outside of that, if you're less than 2 standard deviations below the mean, that happens very infrequently. That happens less than about 2.5% of the time. Where am I getting that number? Well, 100% minus 95.4, that's 4.6%. So what it's saying is that if you have a score that is lower than 2 standard deviations or more than 2 standard deviations above the mean, then you're part of this 4.6%. 2.3% of that is above 2 sigma limits, and 2.3% would be below 2 standard deviations below the mean. So if you have a score or a grade that's lower than 2 standard deviations below the mean, that's a problem. That's a red flag. Even probably if your score is below 1 standard deviation from the mean, that's a little red flag. You should reflect on what needs to be done to get a little bit higher. When my daughter asked me when we first moved to Texas, we were at a laundromat. We put in $1 for the dryer, and automatically 48 minutes popped up on the dryer. She said, why is it 48 minutes? I think she was expecting it to be a round number like 60 minutes or something like that. The answer to this question is not chance. The people who decided that are businessmen and women who carefully analyze the data. They look at, on average, how long does it take for an average load of clothes to dry, and then they make a financial decision. They don't want the customers to be angry, so they put in the money, $1 for each load. They want to make sure that the amount of time that comes up there is sufficient to dry the average load of clothes. We're not talking about a whole load of wet towels or wet Levi's, but the average load of clothes, how much time is needed. Think about this now. If you put in $1 and you only got 2 minutes of drying time, that would be a problem. No customer would use that. They would go to the laundromat down the street because with only 2 minutes, the load of clothes wouldn't dry. On the other hand, if you put in $1 and you got, 3 or 4 hours of dry time, well, the customers would be happy, but the company would lose money because it costs energy to run those dryers. So this is a business decision that takes some analysis, and it's not left to chance. By the way, if you did this with 100 loads of laundry and you plotted exactly how much time it took to dry each load, you would see a normal distribution. How about in the warranties, like some tire companies give a warranty, if the tire wears out or blows out before a certain mileage, that they'll give you a new tire. Again, the numbers that are in those warranties are not left to chance. These tire companies do not want to be in the business of giving out lots of free tires because that costs them money. On the other hand, they don't want to give you a warranty that says, we'll replace your tires if they blow out after 10 miles or 20 miles, because that would be a vacuous kind of warranty. No, that would be no big deal. No, tires don't blow out that soon. They don't wear out that soon. So the company has to make a decision about exactly what number they should put in their warranty. Should it be a very high, outrageous number like 2 million miles? You know, who would care about that warranty? Because you're not going to drive a single set of tires 2 million miles. Or some very low number like 10 or 20 miles. Same thing. In one case, the customer is very happy. You know, if you get a warranty that says we will ensure your tires go at least 2 million miles, that customer is very happy. But that company goes bankrupt because they end up replacing too many free tires. If the warranty has a number that's too low, well, that customer is, you know, not happy at all and probably doesn't care at all about that warranty and probably goes down the street to a different tire company because, you know, there's a suspicion if you're only giving me a warranty for a tire it's going to last 10 or 20 miles, then that tire might be defective. So the company has to choose a number in the middle, and that choice is not left to chance. It's very careful analysis of tire wear and tear. It happens, by the way, that tire wear and tear is normally distributed. We will have a related problem to work on later in the term. My last example before we get into the weeds of the homework is about a close colleague of mine who worked with me in Wisconsin. She had a degree in economics, and over time she became aware that all of her peers all of her full-time peers, other business faculty members, had salaries that were higher than hers. There were 10 other faculty members, all full-time professors of business, very similar academic backgrounds, very similar professional backgrounds, very similar duties at the school. She came to know the exact salaries of each one of her peers. You know, they would go out to have dinners or drinks together, and over time, they let slip how much they were making. And she realized that out of the 11, she was number 11. And in a big way, the grouping was not a tight grouping. She knew, much below number 10. And so she came to my office. I was working as director of institutional research, and she said, you know, what should I do? And I said to her, he's a very close friend. I said, you know, I can't discuss with you the salaries of other employees. First of all, I don't know them, but even if I did, that would be, you know, a big mistake on my part to talk with anyone at the school about other people's salaries. But what I said to her was, go to the president's office, explain your concern, and then when you're done, that president will come to me and ask me to do a related study. And then we'll know if there's a problem. Well, she did that, and 2 minutes after she exited his office, he came to my office and said, you know, we may have a problem here. Can you investigate it? I said, sure. Played dumb a little bit. I said, tell me about the problem. He explained it. I said, well, I'm going to need to see the salary data. He said, fine. I said, no, it's not fine. If I go to the director of HR, he's not going to give me the salary data. You're going to have to ask him to give me the salary data so I can do the analysis. Soon thereafter, I had the data in my on an Excel spreadsheet. I first of all just sorted it from high to low, and yes, it was apparent my friend was way low. She was absolutely right in how much her peers were making relative to herself. The next thing I did was I calculated the average and the standard deviation. My friend was way, way lower than 2 standard deviations below the average, something that happens almost never. In fact, it was something like 2.85 standard deviations below the mean. So I did a little more analysis and some hypothesis testing that we'll discuss later this term, and I walked into this president's office and I said, sir, you have a problem. This is going to go to court and you're going to lose big time. And I explained it with graphs, with percentiles, with standard deviations. I said, now let's call the attorney in. There was a school attorney. And then the two of you, the president and the attorney, can discuss how best to proceed, but I think you better correct this. And indeed, they right away, they did. My friend got a very nice raise, and they paid her back pay for the last 10 years. In this case, there was not really discrimination that was intentional, but she had been hired 15 years or so before that, and when she was hired, she didn't have her PhD finished yet. So she came in at a lower base salary than the others. And then after she completed her terminal degree, she got the same exact percentage raises that her peers did, which was fair, but you see, she was getting that percentage raise off of a base that was lower. So over time, there was a growing gap between her salary and the salaries of others. So not only did she get a raise, but they paid her the back pay that she was deserved for those prior years. so that there was more equity. This stuff that we study this week has lots and lots of very practical, everyday application. In the doctor's office, in the courtroom, in the business office, it's really important. So I really want you to appreciate that fact, and then step by step learn how we can use the standard normal curve and normal distributions to inform our judgments as businessmen and women. There are lots of good videos on the internet about this, but I'd ask that you do that for later viewing. Stick close to what I put on the course shell so as to avoid related confusion. Remember to answer each part of each question assigned, please. There was a question a couple weeks ago about, what do we notice from the two data sets, one on men and one on women. The answer to that question is, well, women live longer than men in this study. But very few of you actually wrote that. You did the work, but you didn't give me the conclusion that was specifically asked for in the question. So from week 3 on, I want you to read each question carefully and be sure to give me a very specific answer to each specific question. And continue to ask me questions on the Blackboard course shell or by email messages or text messages, or when we talk on the phone, make sure I know what your questions are. They're very helpful to me. In fact, several of the questions that I've been asked in the last 48 hours I tried to address in this video. Okay, let's go to the first question of this problem set. It has to do with these 6 receipts. These 6 receipts you have seen before. The employees are, going to ask for reimbursement. And the question for this problem set is, what are the z-scores for each of these 6 receipts? What are the sigma limits, 1, 2, and 3 sigma limits? What do we notice about that result? And is a $190 receipt an outlier? Why or why not? The first thing we have to do here is to compute the average receipt. We did this before, so I'm going to kind of go through this a little bit quicker. That's our average right there. $134.50. That's the average from this sample of 6 receipts. By the way, it is a sample, so in this case we won't be talking too much about Greek letters like mu. In this case it's going to be X bar because we're dealing with a sample. X bar, it's really, if I had a way to do it, I would write X with a bar over top of the X. I don't have a nice way to do that on my keyboard here, so I'll just call it X bar. And generally, whenever you're inside a stats textbook, if you see a bar above some variable like X, it's meaning the average of the sample. And since we're dealing with a sample, when we talk about variance, it'll just be S. When we talk about standard deviation, it'll be S squared. Oh, I'm sorry, I got that backwards. Variance will be S squared. And standard deviation will be denoted as S instead of sigma or mu. Okay. All right, so the averages is 134.50. I think you know how to do this by hand. If I didn't use the Excel formula, we would say equals, and then we would add each one of these up, right? This is how we do averages. And then we would divide. What would we divide by? In this case, we would divide by 6 because there are 6 receipts. So we get the same result whether we do it by hand that way or using the Excel formula. Variance, in this case, it equals VAR, I'll say .S because it's a sample. Left parenthesis, highlight the data set. We get $276.7 squared. Crazy thing to say, but that's what it means, $276.70 squared. And the standard deviation is just the square root of that result. You may recall this is $16.63, period, because we've taken the square root. I'm going to take just a few minutes to do this by hand because I want you to remember what standard deviation and variances are, and I want you to understand the formula, how it works. Remember, both of these measures are measures that tell us how much dispersion there is. Of these 6 receipts, are they all of them very closely grouped, or are they far apart from the average? These measures of variance and standard deviation give us some idea of how close together the data set is. A lot of scatter or not? A lot of spread or not? A lot of dispersion or not? Those are all the same question. I've just used different words. Dispersion, scatter, spread. But in the end, we're trying to figure out how closely grouped are the data sets. Or another way to say it is these curves. How peaked is the curve? How tight is the curve? If it's very flat, that's one thing. That would be standard deviations that are higher. If the standard deviations are lower, then we get a peaked curve. And it matters. In business, it really matters. So for each one of these standard normal curves, we're going to first compute the average, and then we're going to compute the standard deviation. So we have an idea of what the shape looks like. How tall is it? How peaked is it? How far up, or is it flat? Okay, you'll see that this is important. Anyway, to do that computation, you'll recall that the first step is to compute the mean. And then the next step is to figure out how far away each of these individual receipts are from that average. So the first receipt is $22.50 above the average. The second one is $2.50 below the average. And I'm going to continue on here. You've seen me do this in one of the prior videos. It's the first bit of the equation that we talked about for computing standard deviation. So these are what we call the distances between each receipt and the average receipt. I'm going to give myself a little bit more room here. Now, some of these receipts are above the average, some are below the average. If we just added them up, as you might be inclined to do, you wouldn't get a very helpful measure. You'd get 0. And you'd get 0 every time with any data set, which isn't helpful. To get rid of that problem, we square these distances. So equals that distance, caret 2, this distance, caret 2. You say you don't like the caret, you want to do it that times that. That's okay. B4 times B4, that's the same as squaring it. That's fine. But I would encourage you to use the caret. By the way, once you have, because if you use the caret, you can also, if you're taking the cube or the fourth power, all you have to do here is put whatever the exponent is that you want. By the way, once you get the formula put in the cells, you can just click on the lower right-hand corner of the cell and then drag it down, and it will automatically do that computation for you. So now all of these values are positive because we've squared them. And now we can add up all of these. We end up getting 1383.5. Again, I'm going to give myself a little bit more room to work here. And going from the formula, if we take this divided by n minus 1, and n is the number of units in the sample. In this case, there are 6. So n minus 1 would be 6 minus 1. We end up with the variance, 276.7. Now, the variance in the textbook, you get that formula where you have x bar minus mu squared divided by n minus 1. I just applied the formula here. You see I end up getting the same result as I did when I used the Excel formula, $276.7 squared. And then if I want to, again, if I take this, oops, if I get the square root here, you'll see I end up getting the same result. My point is, we can use the Excel formulas, we should, only after we understand them. I want you to know what's happening behind the scenes. What we've done here is we've looked at each receipt, we've looked at how far away that receipt is from the average, then we've squared those distances, then we added them up and we divided by n minus 1 to get the variance. But the variance is hard to talk about because the units are dollars squared, so we prefer the standard deviation. And in this case, when we take the square root, we get $16.63. So now we have an average and a standard deviation. We are now ready to look at the curve. Okay. And I think what I'm going to do here is, well, let's yeah, let me get this. I'm going to copy this picture. I'm going to move it over here. I want you always to kind of keep this picture in mind as we're doing this work. So we know in this case that the average receipt we just computed x bar, not mu. X bar is $134.50, right? And we just figured out that S, or the standard deviation, is $16.63. I want you to start thinking about overlaying that information onto this graph. So this center line here would be $134.50, and we can determine where exactly 1 sigma, 2 sigma, 3 sigma limits are. Here's how we do it. I'm going to jump over here to part B. Okay, so 1 sigma limit, 2 sigma limit, 3 sigma limit. Oops, please forgive my typos. Okay, so 1 sigma limit would be the average minus $16.63. We need that minus 1 sigma limit, minus 1 sigma. It would be equals the average minus the standard deviation. Since I already have it in my spreadsheet, I'm going to say equals alpha 11 minus, equals alpha 11 minus alpha 13. So this line here on the graph, minus 1 standard deviation from the mean, would be at exactly $117.87. Now I have to do the upper bound. I'll put here in the title, lower bound, upper bound. Okay. So the upper bound is going to be the average plus $16.63 equals alpha 11 plus alpha 13. Okay, so this limit here, if I were to write it like you might see in the textbook, this limit would be written as we use brackets or parentheses, $117.80 to $151.13, and I hope you can see where I got that from. And I hope you can see sort of how that relates to this curve. This 1 sigma limits that I just calculated are the range that goes from this minus 1 standard deviation to this plus 1 standard deviation. Okay? Which gives us any receipt that's from $117.87 to $151.13. Now let's do 2 sigma limits. We're going to try to get the value of the receipt that's 2 standard deviations below the mean, and then the value of the receipt that's 2 standard deviations above the mean. So the lower bound would be the average minus 1 standard deviation minus another standard deviation. I look at the graph. The average, which is $134.50, minus 1 standard deviation minus another standard deviation. That gets us to $101.23. You say you're thinking about a different formula where you would put equals the average minus 2 times the standard deviation. That's fine. I'm just trying to show you step-by-step Barney style how this would work. Okay, looking at the graph. We're trying to get the number of the receipt, the dollar value of the receipt that is exactly 2 standard deviations below the mean. And now I'm going to get the dollar value of the receipt that's exactly 2 standard deviations above the mean. So I go equals the average, which I already have here in alpha 11, plus 1 standard deviation, plus 1 standard deviation. The average, $134.50, plus one standard deviation plus another standard deviation. Gets me to $167.77. Again, if I were to write that, as I want you to, in the format that we generally use, which is inside parentheses or brackets, it would look like this. Okay. Let's do 3 sigma limits. Equals the average minus, I'll say 3 times the standard deviation, $84.60. That's this minus 3 sigma here. That would be an $84.60 receipt. And then I'll say for the upper bound equals the average plus, not minus, the average plus 3 times the standard deviation. That gets me to $184.40 over here. That would be the dollar value of the receipt that's 3 standard deviations above the mean. I'm going to ask you to fill in that cell delta 26. Tell me what, using this information, just format it inside brackets. Okay. So those are the limits. And again, as we compute the limits, I want you to be thinking about the empirical rule. Now, let's go back to part. Oh, and before I forget, you notice that I tried to use information that was already in the spreadsheet. So, for example, in the lower bound for 3 sigma limits, I wrote equals A11 minus 3 times A13. If I already have the information in the spreadsheet, I like to use it because if I just end up retyping these numbers, $134.50 every time I need it, there's a chance that I could introduce a typographical error. And to minimize that chance, I like to use the information that's already elsewhere in the spreadsheet, so I don't have to keep retyping a number like $134.50. Let's compute this thing called a z-score and try to understand what it means for each one of these receipts. I'm going to copy alpha 2 through alpha 7 into these cells here, alpha 16 to alpha 21. Did you see how I did that? I highlighted the data that I wanted. I hit copy, and then I put it into alpha 16, and then I hit paste. For each one of these, I need to compute this thing called a z-score. What is a z-score? Well, when we talk about z-scores, we're talking really just about how many standard deviations away from the mean a given value is. If I had a receipt that was exactly $134.50, that would be a z-score of 0 because it's exactly 0 standard deviations away from the mean. If I had a receipt that was exactly $117.87, that would be a z of 1. Maybe we should put this, well, I don't have an easy way to do it there. But again, if I had a receipt that was exactly $117.87, that would be a receipt that had a z of exactly 1. If I had a receipt that was $184.40, that would be a z of exactly 3. Let's see if we can compute these z-scores, and there are formulas in the textbook. But what I'd like to do is actually use examples, and then you can go back and look at the formulas. So this $157 receipt, we know that it's above the average. The average is $134.50. The question is, how far above the average is it? Well, it looks like it's more than 1 standard deviation above the mean, because 1 standard deviation would be $151.13, but it's not 2 standard deviations above the mean. It's somewhere in between 1 and 2. Here's how we do the computation. We take the receipt that's in question, or the value, the data point that's in question, and we subtract the average. It's $134.50. And then we divide by the standard deviation. Divide by the standard deviation. In this case, oh, and it's not dollars. I don't want that format there. It doesn't want it to be a number. In this case, this receipt is 1.35 standard deviations above the mean. This is a positive number. So it would be here, somewhere on the graph here, 1.35 standard deviations above the mean. Now think about what we did there. Instead of focusing too much on the formula, which is the receipt minus the average divided by the standard deviation, think about this graph and the fact that, if it were one standard deviation above the mean, it would be here. If it were two, it would be here. What we got here is just a little bit more than one standard deviation above the mean. I'm hopeful that the math itself makes some sense to you when you think about the graph and when we practice a little bit more. Let's look at the next receipt, $132. This is below the mean, just a smidge below the mean. How far below the mean is it? Well, we say equals $132 receipt minus the average, which is 134.50 cents, divided by the standard deviation. This computation tells us it's minus 0.15 standard deviations below the mean, or 0.15 standard deviations below the mean. You see where I have the cursor for the graph? It's just a little bit below the average value. Okay. Let's try a $109 receipt. It's equals, in parentheses, $109 receipt minus the average divided by the standard deviation. Again, this receipt, $109, it's also below the mean, so we should expect a negative z value here. In this case, we get a negative z of 1.53. It's kind of right here on the graph. Okay. You'll notice that here too, we have been able to verify that it is within within two sigma limits. $109 falls between what we have here on row 25, right? And if we put it on the graph, it would show up here, 1.53 standard deviations below the average. How about this receipt number 4, $145? We know that that's above the mean. The question is, how far above the mean? If you know what your score is on a given exam, it's one thing to know that it's above the average, but what you'd really like to know is how far above the average. How far above the average in terms of standard deviations. Okay? So in this case, it's going to be equals $145 receipt minus the average divided by the standard deviation. About 0.63 standard deviations above the mean. So that would be, if I had to plot it, it would be somewhere here. Okay. So I'm going to give you a moment. I'd like you to compute the z-scores for these last two receipts using the approach that I used for these four. I'm hopeful that you get the same results that I just put there and that you understand what it means. This is a little bit more than half a standard deviation below the mean, and this is just a little bit, about 2/10 or 3/10 of a standard deviation above the mean. This is our first practice computing z-scores. We're going to have a lot more practice, and I hope you're tying this into what you read in the textbook, but more importantly, this graph and what we're trying to do here. We're trying to figure out how far away each one of these receipts is from the average. And to do that measurement, we're going to do it in terms of standard deviations. Is it many standard deviations above the mean or below the mean, or is it just a few? And the reason we do that in the end is because of the empirical rule. It's important to know how far away these individual points are from the mean and how far away in terms of standard deviations. These z-scores tell us exactly how many standard deviations away from the mean each one of these receipts is. Now, part C, what do we notice? In particular, what do we notice about all of these z-scores as we think about the empirical rule. Are any of these z-scores more than 2 standard deviations away from the mean? They're not, are they? All of them are within plus or minus 2 standard deviations of the mean. None of them are above 2 or 3 standard deviations away from them. They're all within plus or minus 2 sigma. They are all with between $101.23 and $167.77. This confirms the empirical rule. By the way, it says approximately, but what it really means is at least 95.4% will fall within 2 standard deviations of the mean. In this case, and this gets to something called the Chebyshev's theorem, in this case, all of the receipts in this sample are within 2 sigma limits. So we notice all receipts are within 2 sigma limits. The empirical rule really works. You say, well, David, you knew the receipts, you knew how this was going to come out and hit. That's true, but if you pull data from your own place of business, data that's normally distributed, you're going to find that this works with that data set too. It's not just because I got specific receipts that I knew were going to work out well. We can use data from your places of business to show that this empirical rule really does work. So I want to think about this last question, a $190 receipt. Is it an outlier? Why or why not? Now that we've computed the limits here, and given our understanding of outliers, outliers are generally anything that is above, that more than 2 standard deviations above the mean, but for sure, I mean, statisticians might disagree about this. Some statisticians say if it's more than 3 standard deviations above the mean or below the mean, then that's definitely an outlier. Like Bill Gates' salary. If we put his salary in a data set, he would be so far above the average that it would screw everything else up. It would screw up our calculations about averages. So, and it's important to note when we have outliers because we might have to treat that data differently. In any case, how about a $190 receipt? Is it an outlier? Well, in this case, yeah. Hell yes, it's an outlier because it is more than 3 standard deviations away from the mean. The mean in this case is $134.50. A $190 receipt is much different. It would be out here in this tail. And remember what the empirical rule tells us. This tail has only 0.15% of the data. 0.15% here, 0.15% in this tail, because the curve is symmetrical. 99.7% of the data is going to fall between 3 sigma limits. So any data point that we find that's in one of these tails is really exceptional. It deserves further analysis. A CFO or a person in charge of reimbursements in this HR office would do well not to immediately reimburse this employee. It might be that the receipt is okay. It might be that the employee didn't do anything wrong, but further investigation would be necessary for sure, because this receipt is so unusual. Was this receipt at a restaurant where just the employee went by himself or herself and ordered a lot of drinks? If so, that's a problem, right? Or maybe the employee took a few extra guests out to dinner because the president wanted him or her to do that, in which case, fine, the employee gets paid, no problem. There's no one really broke any rules. But the fact that it's $190 really is exceptional. It's an outlier, and that's not just my subjective opinion. It's now 3 standard deviations above the mean, something that warrants further investigation. Just like my friend, the business professor, her salary was almost 3 standard deviations below the average of her peers. So definitely was exceptional, something that warranted further investigation. I hope that makes sense to you. And now I would like to switch to question 2 about IQ scores. In this case, the average IQ is 100, so that's what I wrote here. The standard deviation is 15 IQ points. And if we wanted to include sort of labels for each one of these values below the standard normal table, the average here would be 100. So in Foxtrot 20, I'll put 100. One standard deviation below the mean would be 100 minus 15, right? Because that's the standard deviation. One standard deviation above the mean would be 100 plus 15. You see where I got those numbers from? Two standard deviations above the mean would be 100 plus 15 plus 15, 130. How about 3? I hope you agree that that's going to end up being 145 IQ points. And 3 standard deviations below the mean, I hope you agree, would end up being 55. Please let me know, think about what I've just said here. Please let me know if it's unclear where I got each one of these numbers from. So one sigma limit in this case would be from 85 to 115. 2 sigma limits would be 70 to 130. And 3 sigma limits would be 55 to 145. Consider that in a courtroom, a person whose IQ is, say, below 70 would not be subject to the same punishments that other people would for the same crime. The death penalty never applies to people with IQs below 70. Never. They're deemed by our laws to have mental capacity that is lower than what it should be to suffer such harsh punishments. This is an example of a standard normal curve that has absolutely application in a court of law. And the judgment that lawyers and medical doctors and psychologists have rendered is that, you know, anything between -2 and +2 standard deviation, that's 95% of the adults, or 95% of the people in our population. As we get into these tails here, we're dealing with a much smaller group of people. So for the part A, we say, what's the z-score for an IQ of 142? It's going to be somewhere between 2 and 3 z's, because 142 is there, right? The question is exactly how many. It's not 2 standard deviations, it's not 3, it's somewhere in the middle. How do we figure that out? Well, remember the formula, or remember the approach, which is equals, we take the IQ score, 142, minus the average, divided by the standard deviation. In this case, it's 15. So we get a z-score of 2.8. That is, the person with this IQ is going to be somewhere around here on the graph. 2.8 standard deviations above the mean. 142 minus 100 divided by 15. This example is the one that I really want you to sort of remember. It's going to be one I keep coming back to throughout the term. It's one I hope you keep coming back to. You don't really have to memorize the formula if you understand where that 2.8 came from. It's 2.8, almost 3 standard deviations above the mean. It's very close to a z-score of 3, which would be 145. Now, perhaps even more interesting, what is the probability of a person having an IQ below 142? We don't have to guess at this. And this is where our z-table comes into play. This is the same table you would find in pretty much all stats textbooks. It begins with a little graphic that says, it reminds you how the table is used. It has a shaded area here in the tail. The way we do it is we pick out the z-score that we're interested in. In this case, the z-score is 2.8. And then we find out what is the probability connected with that z-score. Again, we look at this graph, and then this note, it says entries in this table give the area under the curve to the left of the z-value. For example, a z of minus 0.85, the chance is 0.1977. Let's see if we can find that minus 0.85. The way the z-table is set up is the numbers on the outside of the table are the z-scores. The numbers on the inside are the percentages, are the probabilities. So a z-score of minus 0.85. The first sheet here is negative z values. What's a negative z value? A negative z value is all the stuff over here to the left of the average. So the first sheet is negative z-scores. The second is positive. By the way, in your next stats class, if you have a textbook that has a z-table, it will not show you both the negative values and the positive, because the the curve, the bell-shaped curve, is symmetrical. So if you really understand what you're doing with z values, you don't really need to know the positive side and the negative side. They're related in a way that should allow you to get the correct answers without having both. But in this initial stats textbook, like so many others, they give you both negative z values and positive z values. So to look at this example, z equals minus 0.85, where would we find that? Well, we first go to minus 0.8 on the left side here, minus 0.8, and then we go, look at the columns, headers here. See, it says 0.00, 0.01, 0.02, 0.03, 0.04, 0.05, because this z that we're trying to look up is minus 0.85. So first we find on the left minus 0.8, minus 0.8, it's here. So I'm going to be focusing on this string of numbers, and I'm going to look at this column here, column number 6, because that is, the header is 0.05. So the probability of having a z-score of minus 0.85 or lower is exactly 19.77%. 19.77%. That is the probability that's associated with a z of minus 0.85. 19.77%. That's what's in the example here. For our problem set, we're interested in an IQ of 142. What's the chance that we'd see a person who has an IQ of less than 142? We don't need to guess. We can go to the table. We look for a z of 2.8. We get the same reminder here, how the table is set up. We look for a z-score of 2.8, exactly 2.8. We see that right here, 2.8. And this first percentage is a z of 2.80, because the header, you look at the header for that column, it's 0.00. So this is the z of 2.80, which is in the problem set. That's what we need. So the answer to this first part of the question is the chance of someone having a z, an IQ of 142, or a z of less than 2.8. Look at how the graph is organized here. Less than, this is all shaded, less than, to the left of 2.8. That chance is 99.74%. 99.74%. Any other answer you give me is wrong. It's important that you see where, not just where I got it from, which I'm pointing it to you, but why I picked that out of this table, because I'm looking for the percentage connected to a z-score of exactly 2.8. The answer is 99.74% that would have an IQ, or the probability of an IQ of less than 142. Another way to say this is the probability that z is less than 2.8. The first thing to do is to compute the z-score. The second thing is to check your z-table, and then you should be able to find the percentage there. Remember, the way the z-table is set up is the z-scores are on the outside of the table, the percentages are on the inside. Let's go to part C. What is the probability of an IQ that would be greater than or equal to 142? Well, we figured out that the probability of less than 142 is 99.74. So the answer to part C is going to be 100% minus 99.74, or 0.26%. Whoa, that's a mistake. What did I do wrong? 100 minus point. Give me a minute here. Equals 1 minus. Okay. It's the flip side of the coin, right? There's a 99.74% chance that it would be less than 142. So the chance of being more than, well, whatever that number is, it's got to add up to 100%. This number in alpha 30 and the number in alpha 27 have to add up to 100%. You'll notice that it is 0.26%. 1 minus this percent is 0.26%. That is a very, very tiny number. If you tell me that your IQ is 143, I say, wow, that's outstanding. Very impressive. Fewer than 1% of people have that. Fewer than half a percent of people have that. In fact, it's almost a quarter of 1%. Very tiny number. Do not confuse this with 2.6% or 26%. No, no, no. This is much, much smaller. It's 0.26%. If you got a 0.26% raise next year, you would be very angry because that would be almost nothing. 0.26%. Again, the number in alpha 27 and the number in alpha 30 should add up to 100%. And again, the numbers, all of the data under the graph, the data under the graph, all of it would be 100%. So that's why we know if we can figure out what's to the left of a given z-value, then right away we know what's also going to be to the right. What is the interquartile range of IQ scores? That's part D. And to get that, what we want to do is go back to the z-table, and we want to try to find out, remember what the interquartile range is. That's the amounts would be between the 25th percentile and the 75th percentile. That's what the interquartile range is. We defined that a couple weeks ago. So how do we get that from the z-values? Well, what we want to do is look to the z-table. I mean, we could look at the graph for a moment. We know that between minus and plus 1 standard deviation, that's going to get us about 68% of our data. What we want is the amount, we want and so that would be from an IQ of 85 to 115. That would get us about 68% of all the people in the population. What we want is to figure out what the IQs have to be to get just 50%. Not 68, but 50%. To get exactly 50% of the data, what would those IQs have to be? It's going to be something less than 115 on the upper end and greater than 85 on the lower end. What we want to do is figure out where exactly that is. Well, if I want to get the z-score showing us this 75%, I'm going to go, so it means picking a z-value where 75% of the data would be to the left of that z-value. I'll go to the z-table and I'll look for a percentage that is 75%. Where is that? Where is that? Where is that? Here's 73%. Here's 74%. Somewhere in there, isn't it? So here, this is 0.67 z's. You see, I said 0.67 z's gets me 74.86%. 0.68 z's gets me something a little bit more than 75%. Let's just for a moment pretend that we're talking about 0.67 z's. What the heck is that? 0.67 z's. 0.67 z. If I had a person who had a z-score that was 0.67 z's above the mean, what would that IQ be? The way we figure this out is by, again, reflecting on the formula that we use to get the z value. Remember, it's going to be some number, we don't know what the IQ is, some number minus the average, which is 100, divided by the standard deviation. And I have to solve for x. What is that x going to be? To solve for x, think about the algebra that's needed for that. This 0.67 equals 0.67. So the first thing we're going to want to do is multiply both sides of this by 15. So the next step would be x minus 100. If I multiply that by 15, the left side, if I multiplied that by 15, I would get just x minus 100, and the right side I would get equals 0.67 multiplied by 15. It's about 10. And then I would, to get x all by itself, I would add 100 to both sides. What this is telling me is that an IQ of about 110 is this z-score of 0.67 that I was looking for here. And if I go down by 10, that gets me the lower bound. 10 additional IQ points gets me 0.67 Z's above the mean. 10 less IQ points gets me 0.67 Z's below the mean. This interquartile range from an IQ of 90 to 110 gets me exactly 50% of my population. It's the interquartile range. Notice that I only had to figure out one of them to understand what the other was going to be. I figured out the z-score for an IQ that would be connected to 0.67 Z's. And the reason I picked 0.67 Z's is because that's about 75% of the data under the curve. Why am I interested in that? Well, if I get 75% of the data to the left, that means that there's only 25% of the data to the right of that number, which is my target. I want to focus in on this area under the curve that gets me exactly 50% of the population. It starts at a point on this curve that is exactly 0.67 Z's to the right. I'm sorry, here, 0.67 standard deviations to the right of the mean, and goes over to 0.67 standard deviations to the left. I'd like you to reflect on that for a while. We're going to have a lot more practice, but this is how we can use the z-score, the z-table, and the graph, and what we know standard normal distributions to figure out exactly which people or which portion of the population we need to focus in on. Same thing for part E. This is extra credit, so I won't go into detail about it right at the moment, but if we want to figure out an IQ needed to be in the top 2% of the population so that we can get into this group called Mensa, we would go to the table and look for, remember how the table's set up, it gives you the percentages to the left of a given number. And if I'm looking for 2%, it means 2% above average. So if I want, in the end, if I want to get the IQ that's 2% of the population above the average, for using this table, I'm going to be looking for a percentage in the table that's 98%, because the table is set up to give you percentages to the left of some number. So let's see, 98%. 98% looks like it's about here. 2.06 standard deviations. 2.06 standard deviations above the mean. .06 standard deviations above the mean. If I go there, then it tells me that 98% of the population is below that IQ, meaning that 2% must be above it. So what is that IQ score? 2.06 Z's. Again, we would use the same basic method we used here. X minus 100, we don't know what the x is now, divided by 15 equals 2.06. We try to solve for x there, and that would give us the IQ that we'd have to have if we wanted to apply for membership in Mensa. More to follow. We're going to have a lot more practice on this. I'd like you to reflect on what we just discussed for the receipts as well as for the IQs. Send me your questions, and I'll begin the preparation of further videos covering some of the other parts of the problem set, but also this additional practice. One student told me that when they thought the videos were very helpful, but they were concerned that, you know, in many cases they were just kind of following along. They were getting the right answers because I was sharing with them, but they were worried that they weren't learning it completely. And I understand that, but the reason I'm giving you all this practice and step-by-step instructions in the video is so that you do begin to develop an understanding and appreciation of how it works, so that for the exams, when I don't show you step-by-step instructions, you know, all the practice that you'll have under your belt will allow you to demonstrate related knowledge and skill. So these first two questions are kind of intended to get the ball rolling, get you thinking about how this works, how we can use the standard normal curve and z-scores to make further determinations about, is someone being discriminated against in court? Is what number should we put in the warranty for those tires? How many cereal boxes we should order? This is question 3, so that we don't have a stock out. We can answer all of these business questions using this material. Question 1 is about the receipts. Question 2 is about IQ. I'm going to end this video now and give you some time to reflect on it, practice it, think about it, work through the math, and hopefully in the next 12 to 24 hours you send me related questions or concerns so that I can incorporate those into the next couple of videos. Have a good day, everybody. More to follow. Stay tuned.